let's take a look at this problem. In one of these two scenarios, we can make the x a small assumption, and in one we cannot. I want to look at them. I want to figure out which one we can make the x a small assumption in. And then for the one we can make the x a small assumption, I want to finish it. The one we can't, let's not finish it. We don't need to be doing the quadratic formula again. So take a second here. We've got this decomposition reaction. H2S going to H2H2s and 2H2S is going to 2H2s and an S2. We got an equilibrium constant. Scenario 1, we got a half a liter flask with some H2S in it. Scenario 2, we got a half a liter flask with much less H2S in it. And we're going to get started. So I would like you to write a mass action expression for this reaction. And then maybe stop. And we'll divide the board into two parts. And we'll see which one, scenario 1 or 2, we can make the x a small assumption for. And then we'll talk about why we can't make it for the other one. All right. Here's what we got. We're going to write the mass action expression for this reaction. The equilibrium constant is equal to H2 squared times S2 over H2S. Okay, now, in scenario 1, there were 0.0125 molar H2S in a half a liter flask. That's a 0.0250 molar initial concentration. And then in scenario 2, there was far less H2S. It was 1.25 times 10 to the negative fifth divided by 0.5. That's only a 2.50 times 10 to the negative fifth molar solution. Now, one of these problems is going to allow us to make the x a small assumption, and one is not. And let's figure out which one it is. To make the x a small assumption, you need to take the initial concentration, 0.0250. That's the smallest initial concentration. There is no initial concentration of these. We only have that one. So 0.0250 divided by the constant, 1.67 times 10 to the negative 7th. If we do that for scenario 1, which has more H2S in the flask, we get a big old number, 150,000. 149,700, blah, blah, blah. Let's go over here and do this one. If we take our smallest initial concentration, now it's 2.50 times 10 to the negative fifth, and we divide it by our constant, 1.67 times 10 to the negative 7th. We only get 150. What does that mean? We are not going to move forward with scenario 2. You cannot make the x a small assumption in scenario 2. We did not get a ratio of our lowest initial concentration to the constant of 500 or greater. But in scenario 1, we did get a ratio of our lowest initial concentration divided by the equilibrium constant of 500 or greater. We're going to move on with scenario 1. Okay, so here's what you're going to do. We're going to plow forward only with scenario 1. So x is small. I want an ice table. This ice table is going to have 3 rows in it because we got 3 things in our reaction. So we got H2S, H2, and S2. No initial concentration of those. We calculated that initial concentration. See if you can't. So we only got this. It's going that way to reach equilibrium. See if you can't fill out the C column. See if you can't fill out the E column. Plug that stuff into the mass action expression. You're free to make the x a small assumption. See if you can't find x and get all the equilibrium concentrations. Go ahead. All right. The H2S is going to go down by 2x. The H2 is going to go up by 2x. The S2 is going to go up by 1x. This is going to be 0.0250 minus 2x. This is going to be 2x, and that's going to be x. So hopefully you got that for your E column. What do we need to do now? We now need to plug this stuff into that expression. So we'll do it up here. 1.67 times 10 to the negative 7th equals We got our h2 squared. So that's going to be 2x squared times our s2x divided by the h2s 0.0250 minus 2x. Oh, hopefully you got that far. Now here's the beautiful thing. X is small. So what does that mean? That means we can get rid of all plus and minus x's. So we can get rid of, because x is small, we can get rid of that minus 2x. I always just kind of lightly cross it out. So what are we left with? Well, this is really just over 0.0250. So we're going to multiply by 0.0250. So 0.025 times 1.67 times 10 to the negative 7. That's 4.175. I'm going to round at the end. Times 10 to the negative 9 equals 4x squared times x. 4x squared times x. That's 4x cubed. Now I'm going to jump down here because I'm out of room. Just going to pull this down to here. 4.175 times 10 to the negative 9 equals 4x cubed. Divide both sides by 4. 1.04375 times 10 to the negative 9 equals x cubed. I'm going to let you catch up because we might have to help you find a button on your calculator here. I need to get rid of the cube. How do we get rid of a cube? We need a cubed root. Now, on a TI-83 or 84 calculator, where will you find that? Well, you're going to find that under the math function. So if you hit the math button, let me clear my screen. Well, actually, not going to clear my screen. If you hit the math button, and math is right under second and alpha math, what you'll get, okay, is this option. Now, there is a cubed root option. It is the fourth option. I also want you to look at option 5. That's the x root. If you needed to take a fourth root or a fifth root, you'd have to type a 4 or a 5 in there first. And then you could use that x root function to do that. Okay, so we got a cube. We're going to take the cubed root. So here's what my calculator looks like. I took the cubed root of that answer from above. Okay, and we're going to hit enter. And this is going to tell us that each x is equal to 0.00101. 0.00101. And now that I have the x's, I can pop them in here and solve for these equilibrium concentrations. Around that with sig figs to 0.0230. And of course, we can now check our work. Okay, we can plug these values into the mass action expression and see if we get the constant. So let's give it a whirl. All right, moment of truth. Here we go. And we get, I got 1.79 times 10 to the negative 7 with rounding close enough. 1.7 times 10 to the negative 7 is 1.8 times 10 to the negative 7. Anytime you round that much with numbers so crazy, you're going to be off by a little bit, but it checks out. Those are the correct values.